And so we take some compound like HCl. We want to know the properties of HCl. One of the properties is solubility. Is it soluble? What do you say? For HCl, HCl is a group 1 compound that's soluble. So, we dissolve it in water. Normally, pure HCl is a gas, and that gas is soluble in water, so we make HCl-AQ. The other property we look at is what happens to HCl when it dissolves in water. Does it break apart completely, partially, or not at all? So what do we know about HCl? Does it break apart completely, partially, or not at all? It breaks apart completely because it is a strong acid. Strong acids are strong electrolytes. And so we look at electrolyte properties. And so it being a strong acid is going to break up into H plus and Cl minus. We call that dissociation or ionization. But we know that H plus is very stable in water. Is H plus very stable? Well, why not? Why is H plus fairly unstable? Yeah. So what would you call that? H plus is unstable because? High energy? Kinda. Well, the high potential energy. What high potential energy in a small space means what? It's a lot more reactive. Why is it a lot more reactive? Charge density. That's it. Because of a high charge density. That's what gives the high potential, the high charge density. And so really, if there's any H plus present in water, it immediately reacts with the water to form what? H3O plus. But H3O plus is too much work to have to write that each time. So we're just going to leave it like this, H plus Cl minus, rather than write it as H3O plus. But we know that H plus is not stable. These are physical properties. Solubility and electrolyte, this is physical because, this HCl aqueous is the same thing, and HCl aqueous is broken up into ions, which is the same thing. This is hydrochloric acid, basically. Hydrogen chloride or hydrochloric acid. Those are the two names we get this. Now, let's look at chemical properties. These are two physical properties that we look at. These physical properties we look at when we're thinking about chemical properties. What are the chemical properties of HCl? So for the chemical properties, we got to look, how many different types of chemical properties are there? How many different types of chemical properties are there? There are only three. Three main types of chemical properties. Does anybody know what they are? That's for kinetic energy. There are three types of kinetic energy: rotational, translational, and vibrational kinetic energy. So like kinetic energy, there's three types of reactions. What are the three types of reactions? Well, conductivity is actually a physical property. It's related to electrolyte property. But conductivity, like for example, HCl aqueous conducts electricity. It's a strong electrolyte because it's sequences of ions, but it doesn't change it chemically. It's still, when you conduct electricity, it's still hydrogen ions or hydronium ions and chloride ions present. They don't get destroyed unless you have something called electrolysis occur when you put too much voltage. If you put too much voltage, then there's potential for something to happen. But as long as the voltage is not too high, then we're just going to get electrical conduction. So this is physical property. Gas solid. It's related to gases and solids. But we talked about it should be in your notes. We were talking about it, I think yesterday or the day before. Combustion is a special type of reaction. But the type of, if it's combustion, we call it by its general name. Combustion is a specific example of this type of reaction. What type of reaction is it? A chemical reaction, yeah, but there are 3 types of chemical reactions. Combustion would fall under what type? Reaction type? Redox. I'll put that as number 3. Number 3, we'll put it as redox. And so combustion is a specific type, but there are many different types of redox that occur. And we'll throw those all into redox. Okay, what else? Acid base. I'll put that as number 2. And synthesis, these are all kind of synthesis. All chemical reactions are synthesis reactions because all chemical reactions we're making products. And in the process of making products, like, and so for combustion, we synthesize CO2 and water in combustion reactions. So they're all synthesis reactions in respect. We've synthesized water. So it wouldn't be that these are synthesis and these other 2 are not synthesis. They're all synthesis. So there's a different name that goes into it. Thesis is part of it. Yeah. Metathesis. So it's a pen. So what we're going to do is we're going to look at metathesis reactions first. So when we're thinking about the chemical properties of HCl, what are the metathesis properties of HCl? What are the acid-base properties of HCl? And what are the redox properties of HCl? Then we know the chemical properties of HCl. If somebody asks you, what are the chemical properties of HCl? Let's start. Okay, so we start off with metathesis. What are the metathesis properties of HCl? That's 1. And so we're just going to focus on metathesis today. We'll look at acid-base and redox properties of HCl later. But metathesis, this is a fancy name for this. What metathesis reactions are, they're favorable ion combinations. Favorable ion combinations. So let's say I have a beaker of HCl, hydrochloric acid. It's labeled hydrochloric acid, but inside the beaker I'm going to find hydrogen ions and chloride ions. Well, actually, hydrogen ions would be hard to find. Instead of hydrogen ions, I'd find hydronium ions and chloride ions, but again, I'm just going to use hydrogen ion. It's just easier. So those are 2 ions. I have hydrogen ions and chloride ions. So all I do in metathesis is I try to find out what ions do hydrogen ions like. Well, they probably like anions. So what anions do hydrogen ions like? And what cations do chloride ions like? When I think about HCl, the ions are split apart. Why are they split apart? They're split apart because strong electrolyte. The only way to bring these ions together is to force them together. How can you force them together? One way of forcing them together is maybe evaporate off the water. If you evaporate off the water, then the pool gets smaller and smaller, and pretty soon the H's and the CL's have to combine. Or sometimes they collide and they just stick together and they are driven off as a gas. But in general, they don't. They don't come together. You know, they're just moving in random motion here, translational motion. And so what are the favorable ion combinations? What do we look for in favorable ion combinations? Well, we look for, okay, what kind of anions can I react with that? What kind of cations can I react with this? There are lots of different anions and lots of different cations, so we have to have a little bit more focus. A little bit more focus is this. You know, what are typical favorable ion combinations? And so things to look for, A, you know, if the ions come together to form an insoluble solid, that is, insoluble solid. In other words, precipitation. That would be good. So if we go to hydrogen ions, hydrogen are group 1 ions. So are there any insoluble solids that are formed from group 1 cations? And you go, well, group 1 and ammonium are all soluble. Therefore, they're not going to come together to form anything. So these are all soluble. And so no matter what anion I mix with H+, it's not going to come together and form a precipitate. However, chloride's a little different. And so when we think about chloride, and we think about the solubility rules. The solubility rules, we start off with a cation. Group 1 and ammonium are all soluble. Then what? Then we look for the anions. Nitrates, acetates, and chlorates are all soluble. Well, we're not nitrate, acetate, or chlorate. We're chloride. And so we go to the next set of anions. And the next set of anions would be chlorides, bromides, and iodides are all soluble except for silver. Okay, chloride with silver ions, lead ions, silver, lead, and mercury. And so this is lead 2, and this is going to be mercury 1. Chloride with silver, lead, and mercury will form an insoluble solid, i.e. a precipitate. In other words, you know, when we have an insoluble solid, what's the difference between an insoluble solid and a soluble solid? An insoluble solid, the lattice is not broken apart. The lattice stays intact. In a soluble solid, the lattice is torn apart, ion by ion, by water molecules. And so how come some lattices can get broken apart, others don't get broken apart? What's that? Yeah, some lattices are stronger than others. And what makes the lattice stronger than others? It's the charge. You know, the higher the charge, the stronger the lattice is, because, you know, what holds the lattice together are the attractions between the cations and the anions. And if the attractions are very, very strong, then the lattice is going to be very, very strong. And if the lattice is very, very strong, then it's going to be really hard to break it apart to get it in solution. Okay, let's try that time. All right, so here's the lattice for sodium chloride. And sodium chloride is soluble, and it's a strong electrolyte. So it's soluble, so the lattice is going to be broken apart. is the bonds. What holds the lattice together with electrical attractions. These electrical attractions we call ionic bonds. Ionic bonds are what holds ions together. And it's the positive and negative attraction. And so this lattice is held together by ionic bonds. The ionic bonds of sodium chloride are kind of weak. And so if I put sodium, in here, well, they aren't going to come together. The ions aren't going to come together and stick and form a lattice like that because the waters will keep them torn apart. The only way to get salt crystals to form in solution, so if I had aqueous sodium chloride, I'd just have sodium ions and chloride ions rather than hydrogen ions and chloride ions. The only way to get the sodiums and the chlorides to come together to form a salt crystal is by evaporating all the water. I have to get rid of all. See, what's going to happen is these ions are swimming, and the pool of water is getting smaller and smaller, and eventually when the pool of water dries up, then the ions are forced together. That's the only time they're going to come together, and then you can get a crystal like this. You can get nice crystals like that. Only force them together, but we don't want to force them together. We want favorable ion combinations. Favorable ion combinations are combinations where the ions run into each other, and when they run into each other, they stick together, and they keep sticking together to form a lattice, and that's what we call a precipitate. And so when chloride comes into contact with silver ions, we will immediately form a lattice like that. And so chloride comes into contact with silver ions, we're going to get silver chloride, and the silver chloride is an insoluble solid. That lattice is quite strong. We can see that here. It looks very similar to sodium chloride. It's just the bonds are a lot stronger. You look at that lattice, it looks like the same thing, except the bonds that hold them together are stronger. Now it's a little bit weird because silver is a +1 and sodium is a +1. So what makes it stronger? What makes it stronger are things like the size. Silver ions are smaller than sodium ions, and there are other factors that can come into play. But this is a favorable ion combination, chloride and silver. Well, how does a chloride encounter a silver ion? Well, we got chloride ions here, and so what we have to do is we have to put in silver ions here. But you can't just buy a bottle of silver ions. The silver ions have to come from some other compound. And so an example of this would be, okay, we have our hydrochloric acid here. Oops. We have our hydrochloric acid. Our hydrochloric acid is going to have chloride ions. And then we got to add some silver ions. Well, I need to add something that has silver ions present. In other words, I need to add something that's soluble, for one, and a strong electrolyte, for two. And so an example of that would be something like silver nitrate. If I add silver nitrate, we know that all nitrates, chlorates, and acetates are soluble. And since this is a soluble salt, it's going to dissociate into silver ions and nitrate ions. And so if I mix these two together, then the silver ions that are from this solution can mix with the chloride ions from this solution and precipitate out silver chloride. So this is going to give me silver chloride, which is going to be a PPT. These are aqueous ions here. Aqueous, aqueous, aqueous. And so the silver chloride precipitates out, and what I have left over is just hydrogen ions and nitrate ions. That's what I'll have left over. And so chloride and silver, that's a good ion combination, chloride ions and silver ions. What's another good ion combination? Lead ions. And so before I leave silver, I know that chloride ions will react with any source of silver ions. So what are some other sources of silver ions? Silver nitrate's one. Can you think of another silver compound that's soluble in a strong electrolyte? So nitrates, what else? Nitrates, chlorates, and acetates are all soluble. So I could use silver nitrate, silver chlorate, or silver acetate. Silver acetate is kind of borderline. But I could use any of those as a source of silver ions. how about something like silver carbonate? Or let's go, if I do silver carbonate or silver phosphate, would that be a good source? No, why not? If I use something like silver phosphate, what happens is this. The silver ions are not free to react. The silver ions are locked in or trapped in a lattice. So how can the silver ions go and react with the chloride when the silver ions are trapped in some solid lattice? And so I can't use something like silver phosphate here because that would be a solid. And so the first step would be to free the silver ions from the phosphate, but it's difficult. This is an insoluble. The bonds are very strong because phosphate's a -3. The lattice is very strong. So it's hard for the silver ions to escape. And so, so far we know that HCl will react with silver nitrate, silver acetate, silver chlorate. What else will HCl react with? It should react with any source of lead ions, because we know that chloride likes lead ions. So chloride likes lead ions. What forms? What forms is, yes, Pb and chloride form. How many chlorides do I need? 2. So it's going to be PbCl2, which is an insoluble solid. It's another precipitate. And so it's a white precipitate. I get a white precipitated lead-2 solid. Lead-2 solid is borderline also, borderline slightly soluble. And so what types of compounds, for example, you know, lead-2 acetate, what's the formula for lead-2 acetate? Pb, C2, H3, O2, parentheses 2. That's lead acetate. So I could use lead acetate. I could use lead nitrate, lead-2 nitrate. I could use lead-2 chlorate as a source of lead-2 ions. But could I use lead-2 sulfide? No, I can't use lead-2 sulfide because lead-2 sulfide is a insoluble solid, and so the lead ions are going to be locked in the lattice. It's not to say it won't react, you know, because on the surface the ions could be attacked, of course. So things can happen. But the reaction is not nearly as favorable as something like this, which just yields aqueous lead ions. Here. Yeah. So let's analyze these two reactions in more detail here. Oh, one more. The last one is chloride ions like what? Like mercury 1 ions. Mercury 1 ions are Hg2, 2+. And what forms here? Hg2, Cl2 solid. So we have precipitation. So in other words, chloride is going to precipitate out with silver ions, lead ions, and mercury ions here. Okay, when we analyze these reactions, let's take a look at what's happening with these favorable ion combinations. And so if I have a beaker, this beaker we'll call HCl. What's inside a beaker of HCl? Well, inside the beaker of HCl, we're going to have molecules or ions. So we're going to have H+ ions and Cl- ions. And then what I'm going to do is I'm going to mix that with a beaker of silver nitrate. This beaker of silver nitrate, this is aqueous. This is aqueous here. In this beaker of silver nitrate, what do I expect to find here inside solution? Do I expect to find silver nitrate molecules? No. Do I expect to find mini lattices, silver nitrate? No. I expect to find silver ions and nitrate ions in the beaker. Now I'm going to mix them together. When I mix them together, the hydrogen ions will encounter chlorides, but they already have over here, and nothing's happened. The hydrogen ions will encounter nitrate ions, but it's not a favorable ion combination. the favorable ion combination is here. If silver ions encounter chloride ions, then they're going to come together and form silver chloride, PBT. And so I expect to find solid silver chloride. This whole thing's going to turn cloudy, and eventually the cloudiness will settle. And so I should get a white precipitate of silver chloride along the bottom of the beaker. And what's left? Well, hydrogen ions and nitrate ions, that's not a favorable ion combination. So the hydrogen ions and nitrate ions just stay in solution. Nothing's happened to those because those aren't going to come together as a favorable ion combination. So in essence, what we have reacting is this. It's only the silver ions and the chloride ions that come together to react. And so what we'll see here is this is what we call the CE. The HCl plus the silver nitrate is going to yield silver chloride solid, and what we have left over is the hydrogen ions and nitrate ions, which we'll just call HNO3AQ. HNO3AQ is a soluble, strong electrolyte, because HNO3 is a strong acid. What do we call HNO3? Nitric acid. So that's what we're going to have. This we call the conventional equation. Up here, this is the ionic equation here, with the ions. And so when we look at what's happening with the ions, this is what's happening, or the total ionic equation. And so let me write it down here. In this beaker, we have H plus ions and chloride ions. In this beaker, we have silver ions and nitrate ions. And when we get all these ions and mix them together, the two that like to react are the silver ions and the chloride ions. The silver ions and chloride ions will come together to form silver chloride solid plus, and what we have left over are the H plus ions and the nitrate ions. But we see one thing, that the H plus ions and the nitrate ions, nothing happened to. They're floating around in solution before, and they're floating around in solution after. And so there's been no change with those. And so we have something called the NIE. The NIE, we get rid of those and just look at what's happening. So what's happening is the silver ions combine with the chloride ions to form AgCl solid. Okay, and so the CE stands for conventional equation, the IE stands for ionic equation. Ionic equation, conventional or complete equation. And NIE stands for the net ionic equation. And so in metathesis, we're looking, what's happening with the ions here. And so what's happening are the silver ions, like chloride ions, they're going to precipitate. There. Okay, we'll do the same thing for the lead. Next example, we're looking at HCl. So I'll have a beaker labeled HCl aqueous. There. The HCl aqueous. In a beaker of HCl aqueous, I have H plus and chloride. And then I'm going to have another beaker that's labeled lead-2 acetate. Aqueous. And lead-2 acetate aqueous consists of what in solution? Well, it consists of lead-2 ions and acetate ions. For every lead-2 ion, I better have 2 acetates. Make sure it's balanced. That's what we got here. And then I know that lead and chloride like each other. Because chlorides are all insoluble except for silver, lead, and mercury. So we know silver, lead, and mercury are special. Chloride. But I need 2 chlorides, so I need to bump this up because I need 2 chlorides. Rather than writing 2, I'll just draw 2 HCl's like that. And so at the bottom of this, I should form a precipitate. It might take time to settle to the bottom, but that precipitate is going to be PbCl2 solid. It's a white precipitate. And then what do I have left over? Well, I'm going to have the H plus and the acetates left over, like this. This precipitation we call driving force. This is the driving force. The driving force is why, why something would want to react. Why something would want to react in this case is precipitation. So it's the same thing over here. This PbCl2, this is precipitation. The driving force. Precipitation is just one of the driving forces. I'm going to come back to that. I'm not quite done with that. But I need to write this on the side here. Another one of the driving forces is this combination here. H plus and acetate. H plus and nitrate make what? Nitric acid. H plus and acetate make what acid? Acetic acid. And so I have two of them, so I need to write 2 acetic acids. But there's a difference here. If we have a strong acids are strong electrolytes. Is acetic acid a strong acid? No. It's a weak acid. Weak acids are weak electrolytes. Weak electrolytes only partially ionize, not fully ionize. In fact, weak acids are more molecule than they are ions. Do you remember I showed a couple of slides of acetic acid? When I look at acetic acid, let's take a look at that earlier slide. When I look at acetic acid is a weak electrolyte, like this. And if I look at acetic acid, most of the molecules are not ionized. Here, only some of the molecules. In fact, few of the molecules are ionized. Most are stay intact like this. So if that's the case, then what we do is this. We don't write these separate because this is another favorable ion combination. The other favorable ion combination is H plus likes acetate. H plus likes acetate. You don't have to force them together. Over here, H plus and nitrate, they don't come together. They're going to stay apart as a strong electrolyte. Over here, H plus and acetate come together and bond. Why? Because they like to be as acetic acid molecules. If you count here, this is a molecule, this molecule, this molecule, rather than acetic acid ions. And so the major species over here are not ions. The major species here are molecules. And so what happens here are the other favorable ion combination is H plus and acetate make acetic acid molecules. H plus and acetate make acetic acid molecules, like that. And so that's favorable. It's favorable because these molecules, molecule, acetic acid. There. And so the major species are acetic acid molecules. The minor species are the ions. Well, in this case, when we're doing these types of equations, we only show the major species. So this is the other driving force. The other driving force is phrased differently. This is going from a stronger acid. Stronger acids are going to be more ions type thing to a weaker acid. Weaker acids are going to be more molecules. And so we have two favorable ion combinations here. We have the ones to form the precipitate and the ones to form the weaker acid from the stronger acid. And so that's the other favorable ion combination, which we'll call B. Going from a stronger
to weaker acid. And so, in this case, H plus is like from HCl. And then we have acetate. Acetate can be, for example, from sodium acetate. Sodium acetate is a soluble salt, strong electrolyte, so we're going to have sodium ions and acetate ions in solution. Well, if the H plus encounters an acetate, then that's a favorable combination because that forms the weak acid, or weaker acid, acetic acid. And acetic acid likes to be molecules rather than ions here. And so we have two driving forces for this. We have precipitation and we have stronger acid to weaker acid. So this is favorable. And so what are the acids? I need to post this on Piazza. This is a handout we'll post later today. But here we have the 7 common strong acids. Can you name them? What's the first one? Yeah, perchloric, hydroidic, hydrobromic, hydrochloric, sulfuric, chloric acid, and nitric acid. Those are 7 common strong acids. If it's not one of those, we're going to assume it's weak. So let's go down the list. This is a table of acid strength. Below nitric is HCO plus, which is, what do we name that? Hydronium. But the weird thing is there's no compounds with hydronium, really. You know where the hydronium comes from? Hydronium comes from when H plus reacts with water. Yeah, liquid water. So, but let's say you wanted to go buy some hydronium acetate. You aren't going to be able to buy a hydronium acetate. You're going to be able to buy acetic acid, and you can take that acetic acid and mix it with water, and when you mix it with water, it forms a little bit of hydronium through hydrolysis. And so that's in brackets there. What's this? Well, this one is organic acid. This is a weird name to it. This is called trichloroacetic acid. And so trichloroacetic acid is the strongest of the weak acids on this chart. And then this one. This isn't an acid. This is an acid anion. What's the name of this acid anion? HSO4 minus. Sulfate. Sulfate is SO4 2 minus, so this would be called hydrogen sulfate ion. That's what it's called. Hydrogen sulfate ion is the new name. What's the old name for this? Bisulfate. Bisulfate. So hydrogen sulfate or bisulfate. It's, that for an anion, it's pretty acidic. So this is an acid anion. It's fairly strong. It's stronger than this acid. What's this acid called? H3PO4. Well, what's the anion called? PO4 phosphate. So not trihydrogen phosphate. You should know this. This should be etched into your memory. Ates form the ic acid. Ites form the aus acid. And ides form the hydroic acids. If that's phosphate, then the acid name is phosphoric acid. So this is phosphoric acid. This one is Chem 1B. That one is a more exotic species, but it's not really that exotic. This is iron 3 ions in water. It's pretty acidic, surprisingly. This one you should know though. What is this one? Nitrous acid. This one? Hydrofluoric acid. This one's an organic acid. You probably don't know the name. This one goes by the common name formic acid. Formic acid or methanoic acid, one carbon acid. This one you've seen before, but written differently. This is C2H3O2. C2H3O2. What is that? Acetic acid. This is what we call the structural formula for acetic acid. It gives us a little bit more information than the regular formula. The regular formula for acetic acid is HC2H3O2. Where that structural, this is called the condensed structural formula, because if we look at the structure of acetic acid, it looks like this. 3 of the hydrogens are bonded to carbon, 1 of the hydrogens is bonded to an oxygen. These 3 hydrogens are not considered acidic hydrogens. This hydrogen is acidic, so this is a monoprotic acid. There's only 1 acid hydrogen here. But the condensed structural formula comes from this, CH3, which is this unit here, and then the C. The C is bonded to an O here and an O here, so it's COOH. So CH3, COOH. That's acetic acid. This one in the quotations, this one's H2CO3. What's this acid called? Carbonic acid. Carbonic. Did you know carbonic acid is unstable? Carbonic acid decomposes. And so this is why it's written like this. It decomposes into CO2 and water. So carbonic acid decomposes into the gas CO2 and liquid water. It doesn't live for very long. So this whole entry is water. There are 2 names for this. One name is for H2S gas. H2S normally is in pure form is a gas. And the other name is when it's aqueous, when it's an acid. So what do we name it as a gas? Well, a lot of these acids we don't use. Normally you use a binary molecular compound, so you call this dihydrogen sulfide or dihydrogen monosulfide. But for acids, we don't name it. For acids, we use the ionic name. And when we're naming ionic compounds, we don't use the di, tri, tetra prefix. And so what we call it is
hydrosulfuric.
Okay, that would be its aqueous name, hydrosulfuric acid. Or as a gas, we call it hydrogen sulfide gas. Its ionic name. Dihydrogen monosulfide would be its molecular name. And so for acids, sometimes we'll use it. So hydrosulfuric acid, what's this called? Dihydrogen phosphate. For acid anions, we use the di, to indicate that there are 2 hydrogens here. So that would be, it's not because, we wouldn't call this dihydrogen monophosphorus tetraoxide, would we? No, we wouldn't. So the dye is only for one specific exception in this case. What's this one called? Ammonium. This one has two names. HCN in pure form is a gas. It's a very lethal gas. If it's HCN gas, we would call it what? Hydrogen cyanide. That would be its ionic name, hydrogen cyanide gas. We wouldn't, the molecular name, we wouldn't be able to name it, because the rules fall apart. This is, trinary molecular. So you wouldn't call it monohydrogen, monocarbon, mononitrate. That wouldn't work. So that's hydrogen cyanide gas. When dissolved in water, makes what acid? What's the acid name? Cyanic acid's not correct. Not correct. Hydrocyanic acid is correct. Cyanic acid comes from the anion cyanate, not cyanide. Cyanate is CNO. And so HCNO is called cyanic acid. HCN is called hydrocyanic acid. And so hydrogen cyanide or hydrocyanic acid. This one, what's this called? Hydrogen carbonate. And another name for hydrogen carbonate would be bicarbonate. In fact, the other name for hydrogen carbonate is much more common than that. Where have you seen bicarbonate before? Probably you've seen bicarbonate and sodium bicarbonate. Have you ever read the ingredients of baking soda? Baking soda is made up of sodium hydrogen carbonate, or more commonly known as sodium bicarbonate. So here's a case where the old name is much more common than the new name. Sodium hydrogen carbonate is a cumbersome name. Sodium bicarbonate is a lot easier. This is what it looks like. This is the bicarbonate ion. It's HCO3 minus. This is sodium ion here. This is sodium bicarbonate. So these acid anions are acidic too. Hydrocyanic acid is not that acidic, is it? Just slightly more acidic than bicarbonate. Bicarbonate's more acidic than this one. What's this one? Phosphoric acid would be, all acids are neutral. And so we need to add the word ion. And so we wouldn't call phosphoric acid an ion, we'd call it hydrogen phosphate ion or monohydrogen phosphate ion. That's what we phosphoric acid, this is monohydrogen phosphate, this is dihydrogen phosphate. You might be tempted to call this trihydrogen phosphate, but it's wrong. We wouldn't call this trihydrogen phosphate. We call it either hydrogen phosphate as an ionic compound, or as an acid, we call it phosphoric acid. H3PO4. Phosphoric acid. Is water very acidic? No. The water kind of the border here, but water can act as an acid too, but it's extremely weak. There's things that are even weaker than water, such as this. What would you name this?
Hydrogen.
So hydrogen sulfide ion. Yeah. We have to add the word ion here because there's another hydrogen sulfide. The other hydrogen sulfide is H2S. This one? Ammonia. Hydroxide. Normally hydroxide is a very strong base. Not an acid. Normally we don't think of it as an acid, but here it can act as an acid. Hydroxide is special. Hydroxide can either act as an acid or a base. things that can act as an acid or a base are called amphoteric. And so hydroxide is amphoteric. However, hydroxide would much rather be a base than an acid. Water is also amphoteric, but water doesn't care. You know, it could react as an acid with equal ease as a base. But neither are very good. It's not a very good acid, or a very strong acid. It's not a very strong base. Pretty neutral. Hydrogen gas we don't think of as acidic, and methane gas we don't think of as acidic. These are very unusual. All these are very unusual acids. The only way to get those to react as an acid is if you react those with a very powerful base. Now, one thing that acids have in common is they have a hydrogen ion that they give up. And so if water gives up a hydrogen ion, it can act as an acid. If water gives up a hydrogen ion, it forms hydroxide. If HS minus gives up a hydrogen ion, it forms sulfide. If ammonia gives up a hydrogen ion, it forms that. What's that called? NH2 minus. Does NH2 minus sound familiar at all? A little bit? What's NH2 minus called?
Nitric hydroxide.
No, not nitric hydroxide. Something else. A little simpler name. You might not remember, but hopefully you wrote it down yesterday. Amide. Amide. So if ammonia loses a hydrogen ion, it forms an amide ion. If hydroxide loses a hydrogen ion, it forms oxide. If hydrogen loses a hydrogen ion, it forms hydride. If methane loses a hydrogen ion, it forms something called methide. None of these want to lose a hydrogen ion. And so that means they're very, very poor, very, very weak acids. Whereas HCl, does HCl lose a hydrogen ion? Yeah, sure. The hydrogen ion is lost. I mean, it's independent, right? It's not stuck on there. So strong acids lose hydrogen ions easily. Weak acids have a tough time losing the hydrogen ions. Methane for sure doesn't want to lose it. And so what that means is this. That means these species are what we call the conjugate bases. These are pairs. So methane, methide is a pair. So if we go one way, left, right, it's an acid. If we go right to left, it's a base. What bases do is they pick up the hydrogen ion. So methide, if it gains a hydrogen ion, it forms methane. How much does methide want a hydrogen ion? A lot. And so methide is the most powerful base on this chart, but methide's a very rare species. So I didn't put methide on your list yesterday. I only put amide. What else did I put? Amide's a very powerful base. So it wants that hydrogen ion. Amide. Oxide. Oxide's a very powerful base. It wants that hydrogen ion. It's going to form hydroxide, which is much more stable. Sulfide's a very powerful base. Amide, oxide, and sulfide are much more common. Hydride and methide are less common, although hydride's not that rare. And sulfide and hydroxide, those are the powerful bases. These are the powerful bases. So what we have are the strong bases down here on the right and bottom side. And then we go to weaker bases here. The weaker bases have lower affinity for hydrogen ions. And the weaker it is, the lower the affinity for hydrogen ions. So the weakest, what is the weakest base on the chart? The weakest base on the chart is perchlorate. In fact, all of these are very weak here. Perchlorate all the way to nitrate. Nitrate's so weak, what happens with nitrate is, does it grab that hydrogen ion and hold on to it? No, it doesn't. You know, this is not a favorable ion combination. And so that means it's very weak. Whereas acetate is much stronger. If acetate encounters a hydrogen ion, you know what it does? It reacts with it, bonds and forms acetic acid molecules. And so, it's a difference there. Well, let's go along the list of bases. We'll start off from the strongest and work our way up. And so we already did this: methide, hydride oxide, amide, sulfide, hydroxide. What's this one? The strongest of the weakest bases is what species? Phosphate ion. Phosphate ion. It makes sense. Phosphate's a -3, so it's going to be really attracted to positive charges, like H+. This one? Carbonate. Cyanide. Now, phosphate makes phosphoric acid. Carbonate makes carbonic acid, although this is bicarbonate. Carbonic acid's over there. Cyanide makes hydrocyanic acid. Ammonia makes ammonium. Monohydrogen phosphate makes dihydrogen phosphate if it just gains one H. If it gains two more H's, it forms H3, PO4 with no phosphoric acid. HS minus is hydrogen sulfide ion. It makes hydrosulfuric acid. We go off the base anion, so base anion and name the acid. But we'll just continue up here. So hydrogen sulfide ion, this one's called bicarbonate. Didn't we see these before? We saw these before. We saw these before on the acid side. The acid side's on the left, the base side's on the right. If something occurs on both sides, then it can go either way. It can act either as an acid or as a base. When something can act either as an acid or a base, we give it a special name. What's that special name? Amphoteric. And so all these species are amphoteric because, yeah, we've seen these, because those can be an acid, they can lose a hydrogen, or they can be a base, they can gain a hydrogen. This one is only a base. This one's called acetate. This one's formate. Formic acid forms formate. Formate, the ic acid goes to 8. This is fluoride. What's this? Nitrite. This one you don't know. That one we're going to skip. That one's Chem 1D. This is dihydrogen phosphate, sulfate. If this is trichloroacetic acid, then this must be trichloroacetate, exactly. And then we have water. Water is not really thought of much as a base, and so this is kind of at the limit. And then we have things that are very weak, like nitrate. Nitrate pretty much has no pull for the hydrogen ion. That's why it's a strong electrolyte here. And so those species are exceptionally weak bases, weaker than water. Nitrate, chlorate, hydrogen sulfate or bisulfate, chloride, bromide, iodide, perchlorate. Go up. Now, the favorable ion combination is we want to go from a stronger to weaker acid. Going from a stronger to weaker acid, we have to be able to rank things. Well, we can rank things using a chart like this here, which I'm going to post on Piazza, or chart. The last chart in the room over there is an acid chart. It has a ranking of the acid strength. It'd be similar to this. But something funny happens. when we use this chart, there's a trick to using the chart here. And there's one potential trap, pitfall, and that's called the leveling effect. The leveling effect would be the strong acid have, roughly equal strength in water. So think of water as the proton picker. And so water as the proton picker, water comes and picks the proton up, the hydrogen ion. What happens is the water picks out that hydrogen ion and forms H3O plus, and we're left with chloride. So water is the proton picker. When I say that they all have roughly equal strengths in water, what that means is that water can pick all the protons off these acids without much trouble. And so which acid is easiest to pluck protons off? The acid that's easiest to pluck protons off is the strongest. An acid is something that can give up its hydrogen ion easily. And so that would be, what's the strongest acid on the chart for chloric acid? And so what I'm going to do is I'm going to do an apple tree kind of thing. And the apples are the protons, or the hydrogen ions. And so water is here. Water is going to pluck the apples off the tree. Well, here is the HClO4 tree. Do you think water will have much trouble taking all the protons off the tree? No. It doesn't even have to lift its arm much. Just like that. And then as we go on, what's the weakest of the strong acids? The weakest of the strong acids is HNO3. HNO3, some of the protons are high up. If some of the protons are high up, then it's going to have more work to grab those. But water is tall enough, or can jump. Water can kind of jump up and grab even the highest proton there. And it can pluck every single proton off the tree for nitric acid, right? But when we get to something like trichloroacetic acid, now trichloroacetic acid is getting more difficult. If you get to trichloroacetic acid, water is unable to get every proton off the tree. For trichloroacetic acid, some of the protons are too high. And so even if it jumps up here, it can't reach up. And so some of the protons are going to be left on the tree. In other words, some of the protons are going to be left on the molecule, meaning that we're going to have molecules intact. Some of the protons will be taken off, so we'll have some ions. The weaker the acid, the taller this tree gets. And the taller this tree gets, the more protons are going to be left on the molecule, and the fewer protons are going to be stripped off. And so here, maybe water can get 50% of the protons off. But when we get to acetic acid, when we get to acetic acid, the 99% of the protons are left on the tree. Less than 1% of the protons are plucked. The tree is way too tall. And so it can only get the easy pickings down here at the very bottom. 99% are left. And so that's the leveling effect. The leveling effect are for the strong acids, they're equal in strength, except for H2SO4. H2SO4 is a little bit stronger. Water's a weak base. Water's a weak base. There are more powerful bases that can pluck all the protons off, even the tallest trees. These are very powerful bases here. And so the other thing about the leveling effect is that's for the strong acids. The strong bases is the same thing. Strong bases have roughly equal strength in water. And so what's happening here is this. If a strong base encounters water, it can easily pluck the proton off water. And so amide can pluck all the protons off water. When amide comes in contact with water, we're going to form ammonia because all the protons are going to be plucked off, and hydroxide. And so all the water molecules are going to be stripped of their proton and left as hydroxide. The same thing with sulfide. When sulfide comes into contact, they'll strip all the protons, will be left with HS minus and hydroxide. If we look at these, all these produce hydroxide, therefore we have a leveling effect. Whereas if we take a look at the weak base, the strongest weak base would be phosphate. When phosphate attacks water, it's not able to get all the protons. When phosphate attacks water, it can only get about 60% of the protons. And therefore, all the phosphates aren't converted into monohydrogen phosphate or hydrogen phosphate and hydroxide. And so what we're going to get is only partial hydrolysis, not complete hydrolysis. So about 60% hydrolysis. Whereas these are strong, therefore they go 100% hydrolysis. And so the strong bases have a leveling effect. And so this is the way we use the chart. Which one's stronger in water? Hydrochloric acid or hydrobromic acid? Which one's stronger in water? You'd say they're equal. They're equal. Which one's stronger? Hydrochloric acid or phosphoric acid? Hydrochloric acid's stronger. And so that's the trick to using this chart. We have to know the leveling effect in order to properly rank things. Unfortunately, I have to leave a little bit early today because I have an appointment this afternoon. So do you want to take a break and then end class early, or skip the break? Skip them end earlier. Skip the break? Okay. We'll end earlier today. All right, so when we're going from stronger acid to weaker acid, we just consult the chart. You just got to be aware how to use the chart. Okay, so let's do maybe some stronger acid to weaker acid example here. An example of stronger acid to weaker acid would be something like this. We'll do hydrochloric acid. What's the formula for hydrochloric acid? HCl. And sodium hydroxide. What's the formula for sodium hydroxide? NaOH. Question mark here. Now we're going to look for favorable ion combinations. And so, different ways we can do this, and I'll talk about the different ways we can do this. A lot of these metathesis reactions have a pattern to it, because we're taking the ions, we're looking for ion combinations, and so what we have is we have ionic compounds. The ionic compounds, we're going to have cation A, which would be hydrogen ions, anion B, which would be chloride, and then cation C, sodium, and anion D, hydroxide. So it's an AB plus CD type pattern. These are ionic compounds. So we've got a cation and anion each. And then we're looking for favorable combinations. So what we're going to do is we're going to exchange anions and see if that's favorable or not. If we exchange the anions, then what we're going to do is we're going to pair cation A with anion D and cation C with anion B. So we're going to form. Yeah, this is called double replacement. Double replacement. And so here we're going to take hydrogen ions, but rather than with chloride ions, we're going to pair them with hydroxide. So we'll take hydrogen ions and hydroxide ions. Well, if I have hydrogen ions and hydroxide ions, what does that make? That makes HOH. And then I'm going to take sodium ions and pair those with chloride ions. So if I have sodium ions paired with chloride ions, what does that make? That makes sodium chloride. And then I see, are either of these favorable? Well, HOH, we have another name for that. What is that? Water. So we're going to make water and sodium chloride. Well, the first thing is HOH a precipitate? Is that going to precipitate? No, group 1. Not going to precipitate. How about sodium chloride? Does that precipitate? No, that's not going to precipitate either. And so we aren't going to form a precipitate. Then we look for another driving force. Well, the next driving force is we're going to go from stronger acid to weaker acid. Well, we got a strong acid here. It's HCl. So this is going to be our stronger acid. But the question is do we have a weaker acid on the right? Is there a weaker acid on the right? And that would be water in this case. Water is a weaker acid. And so we're going from a stronger acid to weaker acid. Water is a fairly weak acid. And so if we go from stronger acid to weaker acid, then that's a favorable ion combination. Hydrogen ions like hydroxide ions. They're going to form water. And so this is going to be our driving force here. And so our driving force is stronger to weaker acid. HCl is aqueous, NaOH is aqueous, HOH or H2O is liquid, and NaCl is aqueous. And so the formation of NaCl is not going to do anything because when I look at this, if I have a beaker of HCl, the beaker of HCl contains H plus and Cl minus. If I have a beaker of sodium hydroxide, so aqueous, the sodium hydroxide is going to contain sodium ions and hydroxide ions. And then I mix them together. If I mix them together, what ions like each other? Hydrogen ions and hydroxide ions like each other. Hydrogen ions and hydroxide ions are going to form H2O, liquid. But sodium ions and chloride ions, nothing's going to happen to. And so those are just going to stay in solution like this. And so what we're going to end up with is forming H2O, liquid, plus sodium chloride AQ. Sodium chloride AQ are just the aqueous ions, basically.
Because there's no precipitate, otherwise it would be solid.
Otherwise, it would be solid if this was a favorable ion combination. Sodium chloride is soluble, therefore AQ. Sodium chloride is also a strong electrolyte, which means the ions are totally separate. It's a strong electrolyte, it's dissociated. But in the conventional equation, we write it together. Just like sodium hydroxide. Sodium hydroxide is soluble and it's a strong electrolyte, so the ions are separate. HCl is soluble, it's a strong electrolyte, ions are separate. And so this is called the conventional equation. The ionic equation is what we see in solution. So here we're going to see H plus and Cl minus. Over here we see sodium ions and hydroxide ions. Over here we're going to see water, liquid forms, and sodium ions and chloride ions. And then finally, the NIE, the net ion equation, we get rid of the spectator. So H plus reacted with OH minus. Chloride didn't react. Chloride stays the same. Sodium ions didn't react. They stay the same. Hydroxide ions did react. They react with the H plus. So the H plus reacts with the hydroxide to form H2O liquid. So this is what we call the NIE, or the net ion equation. And the driving force was stronger to weaker acid. What was the driving force? Which we had here, stronger to weaker acid. So this is an example of stronger to weaker acid. That's the driving force. There's one more set of favorable ion combinations that we have to keep in mind. The last set of favorable ion combinations are the gas formers. So let's say BC. Let's see. B was stronger to weaker acid. C is going to be gas formers. The gas formers are going to be like this. So, for example, hydrogen ions and carbonate ions like each other. Hydrogen ions and carbonate ions form H2CO3, carbonic acid. But we know something about carbonic acid. What do you know about carbonic acid?
It decomposes.
It decomposes. It's totally unstable.
Carbon dioxide.
Yeah. So this will decompose into carbon dioxide gas and H2O liquid. So this is a gas former. Also, H plus and HCO3 minus. If we have H plus and bicarbonate, we end up forming carbonic acid, which decomposes spontaneously to water and CO2 gas. It doesn't matter which one you write first. And so this is carbonic acid. Carbonic acid is a gas former. Like carbonic acid, we have H2SO3. H2SO3 is called sulfurous acid. Sulfurous acid forms when two H pluses combined with a SO3 2 minus. SO3 2 minus is called SO3 2 minus is called sulfite. And so if that's the case, we form sulfurous acid. Well, unfortunately, sulfurous acid is just like carbonic acid. It's unstable and will decompose into decomposes into H2O liquid plus SO2 gas. Rather than forming carbon dioxide, it forms sulfur dioxide. Sulfur dioxide is a toxic gas. Watch out. That's acid mixed with sulfite, or acid H plus mixed with hydrogen sulfite or bisulfite. Will form the same thing. It's going to form H2O liquid and SO2 gas. Sulfurous acid, which decomposes. They're gas formers. There's some more favorable ion combinations which form gases. Ammonium and hydroxide. When ammonium ions meet up with hydroxide ions, we form ammonium hydroxide. Ammonium hydroxide, however, is unstable and decomposes. Ammonium hydroxide decomposes into ammonia. Ammonia is what we call polar. CO2 is nonpolar. So CO2 is like oil. Oil and water don't mix, so CO2 and water don't mix. But ammonia is very polar, and so ammonia and water mix pretty well. And so ammonia might be aqueous or gas. Depends how much agitation there is. Normally ammonia is a gas, but it likes water, so it can stick around. And H2O liquid. So ammonium hydroxide decomposes. This formation of ammonium hydroxide, that's another favorable ion combination that's decomposed into a gas. Then we have some more, like this, hydrogen ions. If I take two hydrogen ions and a sulfide ion, that's favorable too. That makes H2S. H2S is a gas. A little bit will dissolve in water to form hydrosulfuric acid, but mostly it's insoluble, or very borderline insoluble. So it's a rottenate, gas. We can use H plus and HS minus to give us the same thing. It will form H2S gas, toxic gas. Other ion combinations that like each other, HCN. So if I have acid and cyanide, you gotta watch out. Never mix acid and cyanide. So let's say HCl. If you take HCl and mix it with sodium cyanide, you're asking for trouble. If you take hydrochloric acid and mix it with sodium cyanide, you're gonna form HCN gas. HCN gas is hydrogen cyanide gas. HCN aqueous is called hydrocyanic acid. Well, hydrocyanic acid is not that soluble. So these are all aqueous. Pretty soon, I get tired of writing aqueous over and over again. So you have an option. What you can do is you can leave off aqueous, but make sure you write everything else: gas, liquid, solid. So from now on, I'm going to leave off aqueous. If it's blank, it's aqueous. But if I do that, I got to make sure I write gases. I got to make sure I write liquids, and I got to make sure I write solids. You don't want to mix acid with sulfides too. You're going to generate toxic gas. So both of these are toxic gases, etc. And so those are favorable ion combinations there. So what we're going to do is we're going to do a couple of examples of this here. We're going to try metathesis reactions. Metathesis, this is called double replacement. A form of metathesis is double replacement. Double replacement is an easy way to check, if we got a good ion combination or not. All right, so let's do this first one here. Solutions of lead-2 nitrate and sodium bromide are combined. What is lead-2 nitrate formula? PB NO NO3 2. Nitrate's a -1, so we'll need 2 of those. Balance out lead's +2 charge. So the lead-2 nitrate. Is it soluble? Yeah. It's soluble because nitrates, chlorates, and acetates are all soluble. So it's aqueous. There's water present. Otherwise it's solid if there's no water present. If it's soluble, do the ions break apart or do they stay together? They break apart. So this is the soluble strong electron. So if we had a beaker of this stuff and it's labeled PbNO3 2, then it consists of lead ions and nitrate ions. 2 nitrates for every lead. That's what we got there. And then we're going to mix it with sodium bromide. What's the formula for sodium bromide? NaBr. And so there are 2 ways we can visualize it. We can just visualize it looking at the ions, pairing up the ions and saying, or we could do this way. We'll pair up the ions by doing double replacement. We'll just swap the ions. So now what we're going to do is we're going to pair lead-2 ion with bromide ion. If we pair lead-2 with bromide, we get lead-2 bromide. What's the formula for lead-2 bromide? Yeah, PbBr2. And then we're going to get sodium ions with nitrate ions. What's the formula for sodium nitrate? NaNO3. Okay, so this is the quick way of just doing this double replacement. Basically, we're doing this. If I got sodium bromide in solution, I got sodium ions and bromide. And so I just look at the combination. I'll take lead ions with bromide and sodium ions with nitrate and see if we get anything to happen. Because as they are right now, the only way to get the leads and nitrates to come together is evaporate the water, and the only way to get the sodium bromides to come together is evaporate the water. But when lead sees bromide, is that favorable? And so we ask ourselves, will lead-2 bromide precipitate? Yes. Lead-2 bromide precipitates. It's insoluble. Chlorides, bromides are insoluble except for silver, lead, mercury. So lead is one of the exceptions. Lead precipitates. And so lead and bromide like each other. And that's going to precipitate out lead-2 bromide solid. That should sink here. How about sodium and nitrate? Does sodium nitrate precipitate? No. Group 1 salts are all soluble. Nitrate salts are all soluble. This sodium nitrate, is it a weaker acid? Was it even on the acid chart? No. Is sodium nitrate going to decompose into a gas, or maybe it's already a gas? No. And so nothing happens here with sodium nitrate. This is not a favorable ion combination. But the only reason I keep it together is because we have sodium and nitrate, and if I evaporate all the water, then I'll get solid sodium nitrate to come out. But you know, this is not balanced, is it? You know, because for every lead ion, how many bromides do I need? 2. To form PbBr2. And so I need 2 sodium bromides. That means I'm going to have to bump up. I'm going to need another sodium and another bromide there. And that's going to give me 2 sodiums left over and 2 nitrates left over here. So I have the 2 nitrates that didn't react. And so by doing a double replacement, we can see. I'll just write aqueous one last time here. Okay, this is the CE, and then we say the driving force. The driving force is precipitation, PPTION, of lead-2 bromide. Then we do the IE. The IE is just looking at the species. The IE is the major species present. The major species present are going to be lead ions and nitrate. You have 2 nitrates for every lead. Major species here are going to be sodium ions. I got 2 sodiums and 2 bromides. And then I have this. I have lead-2 bromide. Lead-2 bromide. Do I dissociate it or do I leave it intact? I leave it intact. In fact, for ionic equation, this is what we're going to do. We're going to ionize only the strong electrolytes. That's going to tell us the major species. So if it's a weak electrolyte, the major species is just whatever it is. And so, for example, here, soluble salt, ionized. Soluble salt, ionized. Soluble salt is a strong electrolyte. Here, this is an insoluble salt. Insoluble salt, leave it alone. Leave everything else alone. So PbBr2. Ionize only the strong electrolytes, leave everything else alone. We got PbBr2 solid. And then we got to ionize that, except this is not balanced. We need 2. So we're going to end up with 2 sodium ions and 2 nitrate ions at the end. And now we'll do the NIE. The NIE, we look for spectators. Did the lead react? Yes, precipitated. Did the nitrate react?
No.
No. And so we can eliminate the nitrate. Did the sodiums react? No, so we can eliminate the sodiums. Did the bromide react? Yes, the bromide precipitated. So the lead-2 plus 2 bromides yields PbBr2, solid. And so this is our favorable ion combination here. Lead ions like bromide ions.
And they're gonna form lead 2 bromide solid.
Okay. Let's try one more here. Hydrochloric acid plus sodium carbonate. Why don't you do metathesis reaction for this? Or double replacement? That works. So give that a try and see. This one, by the way, is from last week's lab. This is like one of the first reactions you did.